we're going to actually move on to the next chapter, which is chapter 16. Chapter 16 deals with solutions. Solutions are homogeneous mixtures. They could be solid solutions like alloys, brass, 18-karat gold, or they could be gaseous solutions like air, or they could be liquid solutions like sugar water. This chapter is going to focus on liquid solutions. It's just homogeneous, uniformly distributed. So let's take a look at these liquid solutions. When we're dealing with solutions, we look for the solute. The solute is the minor component, and the solvent is the major component. And so if these are liquid solutions, we're looking at water as being the solvent, and the solute is whatever you dissolve in the water. What you can dissolve in the water are salts and gases and other liquids. Salts would be like table salt, or sugars, polar molecules would dissolve in water too. Liquids would be like ethanol. Ethanol dissolves quite nicely in water. Gases would be like HCl, dissolves quite nicely in water. So we have the solute and the solvent. And the solute plus the solvent gives us the solution. So let's take a look at some solutes here. This is copper 2 chloride, this blue solid here. And this would be our solute, this would be our solvent. The solvent's water here. This is going to make a solution. So this is just taking some crystals of copper 2 chloride and dissolving in water. The crystals are going to break apart and form the ions. A copper 2 ion here and a chloride ion there. These ions are going to be surrounded by water. So copper 2 is positive, so the negative side of water surrounds it, with oxygen. Chloride is negative, so the positive side of water surrounds it. It's going to completely surround it. We call this hydration or solvation. Hydration being it's water, or solvation, water is a solvent. So those are hydrated or solvated ions. We have concentrated and dilute solutions, but concentrated and dilute is relative. It depends on how soluble it is. Just like humidity, humidity depends on what the temperature is. 100% humidity is not the same. Same amount of water. Here's concentrated versus dilute. This is a light blue color, so we don't have that many copper 2 ions. This is a dark blue color, so we have a lot more copper 2 ions in the solution. This is a single replacement reaction with copper wire and silver nitrate. So these are silver. So when the reaction starts out, we don't generate that much silver here. As the reaction progresses, we start generating lots of silver. These silver crystals here. As this silver nitrate attacks the copper gets oxidized in copper 2 ions, which go into solution. This is that over here. Well, concentrate and dilute depend on what's its solubility. Some things are very soluble, some things aren't that soluble. The solubility varies. There are two definitions of solubility. One is the qualitative definition. Is it soluble or insoluble? And so, for example, group 1 and ammonium salts are soluble. But there's a more quantitative definition. Yeah, okay. Does that mean an infinite amount of salt will dissolve in water? No. Even though salt is very soluble in water, we can't dissolve an infinite amount. There's a limit, and that limit is called the solubility. For table salt, that limit is about 36 grams. We can dissolve 36 grams of table salt in 100 milliliters of water. If we tried to dissolve 37, only 36 grams will dissolve. the 37th gram, that last gram will stay as a solid. It won't dissolve. And so that's the quantitative definition. The quantitative definition is exactly how much will dissolve. You know? Versus the qualitative, well, heck, it's pretty soluble. Well, if there is a limit, then we're going to have something called a saturated solution. So 36 grams of table salt and 100 milliliters of water is completely saturated. We can't get that 37th in there because it's totally saturated. But let's say it could be unsaturated. So for example, if we had 100 milliliters of water and we only put in 5 grams of table salt, then no problem. There's still plenty of capacity to dissolve more, so that would be unsaturated versus saturated. We could also have things that are supersaturated, but the things that are supersaturated are unstable. You know, sometimes you can get more to dissolve than what's sustainable. So an example of that would be, you know, like sugar. Sugar in cold water versus sugar in hot water. Solubility is different. In hot water, sugar is a lot more soluble. But what happens is if you dissolve sugar in hot water and then you cool it down, then the solubility goes down. As the solubility goes down, the excess sugar should crystallize or precipitate out. But sometimes that crystallization process is lagging. That is, sometimes crystallization isn't so easy. And there's a bit of a lag period. And during that bit of a lag period, the sugar water is super saturated. And the reason for that is sometimes it's hard to nucleate crystals. Nucleating crystals means starting a little baby crystal. Sometimes that's hard to do. And so let me show you some classic examples of supersaturated solutions here, just from video. This is demo. But one thing that has a hard time nucleating baby crystals is sodium acetate. This is the shape of the acetate ion. And take a look at it here. Take a look at some demos. Take one of these.
I have here is a supersaturated solution in this big 1 liter Promar flask. And what I'm looking to do is hopefully, if I made this right, be able to show how the supersaturated solution actually will come out of the solution as I pour it.
All right. So to make this supersaturated solution, they heated it up. But they heated it up and dissolved a heck of a lot of sodium acetate in there. But when it cooled down, it was hard to nucleate little baby crystals. And so there are different ways you can help it nucleate little baby crystals. One is you could drop something called a seed crystal in there. If you drop a seed crystal, then it gives a template for crystallization. Other ways is if there's scratches. If there's scratches in here or if there's dust in here, that could help seed crystals. And so actually this is kind of a long video, so I'm going to fast forward it here. Okay. That was a lot of talking. All right, another is to provide a surface. So I guess on this piece of wood here, maybe the crystals can start to grow. Here.
Demonstration, so let's see what happens.
There. Once a crystal seeds, then the other crystals can grow on top of it.
Good. Well, now it's going back into the beaker.
is that a beaker? No, it's not a beaker. What is that? It's an Erlenmeyer flask. That's a little bit annoying. But you can see, do you see the crystals starting to grow inside the Erlenmeyer? That's what's happening. So there's a huge difference in the solubility between hot water and cold water. In cold water, barely any sodium acetate dissolves. In hot water, a tremendous amount of sodium acetate dissolves. And having that huge discrepancy makes sodium acetate the ideal candidate for supersaturated solution.
So that little bit of water is able to dissolve.
There are other ways to seed, like for example, seeding gas bubbles. And so this is the this is going to be Diet Coke and Mentos. Actually, I want to video this. Maybe we'll see the rocket here. Which one do you want to see? Let's see the latest one.
Today, we're here for
I'm gonna skip it there. All right. Diet Coke. Diet Coke, what happens is, you know, what's inside here? Is that air? This is not air in here. You know what this is? It's pure 100% CO2. That's right. Yeah. And so what happens is the CO2 gets forced in there, and then it creates something that we call dynamic equilibrium. The CO2 is in equilibrium with the Diet Coke. So this is just CO2 of 1 atmosphere. But when we remove this, what happens? Well, the CO2 is going to escape, and it's going to be replaced with air. Well, how much CO2 is in air? So we go from 1 atmosphere to about 0.05 atmospheres or something like that. And so all of a sudden, there's barely any CO2. And so what that's going to mean is there's way too much CO2 in the liquid here. And so it's super saturated in CO2 if we remove this. The reason all that CO2 doesn't just crystallize out of there or bubble out of there immediately is because of nucleation of bubbles. So Mentos provides a surface for bubbles to nucleate and grow. And so they got a lot of Mentos there. Let's see what happens here. I don't know why she's laying on the ground. Okay, so let's try to skip this and go right to. Is that too far? Okay. All right, so they made a little tube to drop the Mentos in. So this is super saturated. Eventually the bubbles will nucleate and get out of here, but they want to speed it up. Well, one way of speeding it up is seeding it, and they're going to seed it with the Mentos. It's going to help nucleate bubbles. And when that happens, you'll see how super saturated this is, like the sodium acetate. Well, let's see if they have something a little better. What happened to that little go-kart? Yeah, unfortunately. It was a Photoshop. Okay, unfortunately that wasn't. There was no go-kart there. I was excited. I'm kind of disappointed. 30 miles an hour. I wanted to see that. They have ones that do shoot up. But I don't know. I don't trust that one there. But they have ones that shoot up like hundreds of feet into the air. So I'd like to see that video. Yeah. But there's so many. I should save it. But I didn't. Sorry. Yeah. Okay, Mentos rocket. It's really surprising how high it goes. Well, this one's 100 feet. So let's try this one. Hopefully this is accurate. I don't know if that's 100 feet. Would you say that's 100 feet?
Like 40. Does it have to be Diet Coke?
Well, unless you want to get it all sticky everywhere with a regular Coke or something. But Diet Coke seems to work better. Plus Diet Coke, you know Diet Coke weighs a lot less than regular Coke. Because regular Coke has lots of grams of sugar in there. So it weighs a lot less. It's less dense. Diet Coke's less dense than water. And so there's a lot of reasons to use Diet Coke. But it doesn't have to be Diet Coke. It could be any soda. Maybe soda water. That'd work good. Okay. Well, that's a supersaturated solution. Here. Okay, I don't know why they divided it like this. Slide, but so we have unsaturated, saturated, and supersaturated. These are two more terms that are describe solutions. If there is no limit, let's say you could dissolve an infinite amount. For example, we can't dissolve an infinite amount of salt in water, but you know what we could dissolve an infinite amount of in water? No, sugar is going to reach a solubility limit. Do you know what the solubility limit of sugar is? I don't, so I'm kind of curious what that is, and where can we look it up? Well, actually, it's going to be on Wikipedia. So sugar is called sucrose. We could look it up on Wikipedia, we could look it up on, there are a whole bunch of other sites we could look it up on, or data books. But Wikipedia is pretty good for this kind of stuff. Yeah. So solubility is given here in water. So at room temperature, 25 degrees C, we can dissolve 200 grams of sugar in a deciliter. What is a deciliter? 100 milliliters, I guess. That's a lot, 200 grams, but it's not infinite. And so we can dissolve a heck of a lot of sugar. But what can we dissolve an infinite amount in water? Not sugar. Let's take a look at the solubility of ethanol. When you look at the solubility of ethanol in water, it says it's miscible. So what does miscible mean? It means it's infinitely soluble. It means there's no limit to how much ethanol. In fact, you can put so much ethanol in water, pretty soon you have to stop calling it water because it's like 99.99% ethanol and just a tiny amount of water. And so all of a sudden it flips. We pretty much flip. When we get to about 50% ethanol, we'll still call it a water solution. But when we get more than 50% ethanol, we should start calling it an ethanol solution. We dissolve the ethanol in the water, not the water in the ethanol. Does that make sense? And so miscible means infinitely soluble. Yeah, totally. Or you could have 100% alcohol. So you can put a little bit of water in or lots of water. And so miscible. You know what immiscible is? It's the opposite. And so immiscible means it's insoluble. So ethanol likes water because they both hydrogen bond. Ethanol hydrogen bonds, water hydrogen bonds. But oil, does oil like water? Oil hates water. You know? And so oil is immiscible. They don't mix. And so immiscible things don't mix. Here, looking at sodium acetate again, but they're dropping, this is called a seed crystal. So the seed crystal just provides a template, making it easier to crystallize things. They drop the seed crystal in there and it rapidly grows. They form sodium acetate crystals. This is super saturated sodium acetate. Here's miscible and immiscible. Oil, however, does like carbon tetrachloride. Carbon tetrachloride is nonpolar. So if we have something like gasoline, octanes in gasoline, if we have some gasoline and mix it, or oil mixed with carbon tetrachloride, they like each other and therefore they're miscible, solvent, all proportions. But if we take oil or gasoline and try to mix it with water, it's immiscible. In this case, the gasoline's less dense. Surface. So they don't like each other. And so this brings up like dissolves like. Nonpolar likes nonpolar molecules. And these are unlike because this is nonpolar, this is polar. So they don't dissolve each other. Gasoline is made up of hydrocarbons, a mixture of hydrocarbons. Gasoline's not a pure substance. So we're going to look at the formation of a solution. When we look at the formation of the solution, we are looking at these interactions here. So I'm going to skip this slide here. And we'll just take a look at the steps of solution formation. We'll skip this slide. This slide. And so if we look at these ions are charged. Water has charges. Water is polar, and so like the positive cations, the negative end of water, which is the oxygen, likes it, and the negative anions, the positive end of water, likes it. So water can attack this, because one end of water is negative, the other end is positive, so it can pull apart this salt here, and we make the hydrated ions like this. If this is unsaturated, then the water is going to completely dissolve this until it becomes saturated if we have enough salt. And then if we try to add more salt to it, then it won't dissolve. But the interesting thing is, let's say we add more salt to this, and this is already saturated. What happens is the crystal doesn't stop dissolving. The crystal is always going to dissolve because of these collisions with water. But at the same time, the ions might come back here and stick. If the ions come back here and stick, then we'll form more crystal. And so when this becomes saturated, we have what's called a dynamic equilibrium. Dissolving continues and crystallization continues. And so this is it. When the solution's unsaturated, we have net dissolving. Net dissolving is given another name. It's called dissolution. So we have net dissolution when it's unsaturated like this. As the solution becomes more and more concentrated, what's going to happen are the ions can come back and strike the crystal and stick. That is, crystallize like the sodium acetate did. That's why we have the C there. Once it becomes highly concentrated, then what's going to happen is the rate of crystallization will equal the rate of dissolution. When these two rates are equal, then nothing appears to change, and we're at equilibrium. But it's called a dynamic equilibrium because the crystals never stop dissolving, and crystals never stop crystallizing. So this is going in circles, it's churning here. It's a dynamic equilibrium. This is called dissolution. This is formation of a saturated solution. So what determines how soluble something is? What determines how soluble something is are the strength of the forces holding the solute, solvent, and solute and solvent together. In other words, the strength of the forces of the solute, let's look at that. It doesn't have to be intermolecular, it could be bonds. So how strong are the bonds in the salt? If the bonds are too strong in the salt's not going to dissolve. This is why things like phosphate has strong bonds because -3. Carbonates aren't soluble, oxides aren't soluble because they form strong ionic bonds. Whereas group 1, ammonium, nitrate, acetates, chlorates aren't that strongly bonded, so those break apart. So it depends on the strength of the bonds. Then, in order to make room for these hydrated ions, we have to break apart the hydrogen bonds and replace those with these. These are called ion dipole attractions. And so if the ion dipole attractions are about as strong or stronger than the hydrogen bonds, then these will form favorably. Oftentimes these ion dipole attractions are quite strong because it's a partial positive charge on the hydrogens being attracted to full negative charge. And it's a partial negative charge on the oxygens being attracted to full positive charge on the ion. And so these ion dipole attractions can be quite strong, stronger than hydrogen bonds. And so this is the dissolution process. We look at breaking apart the solute, we look at breaking apart the solvent to make room for the solute particles, and then we look at the attraction that forms between the solute and the solvent. So, and if the energetics are favorable, then it should dissolve. If the energetics are highly unfavorable, then it shouldn't dissolve. And so this is why factors that determine solubility is the strength of the forces in the solute, solvent, and solute and solvent. It's the partial pressure of a solute gas over a liquid. And so the CO2, the more CO2 you push on top of that liquid, the more that's going to get forced into the liquid. So if we put 1 atmosphere of pure CO2, we can force a lot more CO2 in the water than 0.05 atmospheres or less. It's a lot less. 5%. That's 0.0005, something like that. The temperature. The temperature is going to dictate solubility. So, for example, sugar or sodium acetate at high temperature, we can dissolve a lot more. However, gases at high temperature, we can't dissolve more. We can only dissolve less. Unfortunately, I have to leave early today, so I'm going to stop here. We'll talk more about this next time.